Hey guys, today we're looking at differentiating exponentials. So, all I've written here in blue so far is that the derivative of e to the x is e to the x, okay? So, that's our first base point. Remember when we first started looking at differentiating, say I was looking at y equals x squared. If we were to take the derivative of that, we say dy dx or y dash is 2x to the power of 1. Because we take the power, times it out the front, and then we subtract 1 from the power. Well, now let's look at that in terms of exponentials. Straight away, if I gave you just e to the x, technically what I'm doing is I differentiate the power, which is just the derivative of 1x, okay? So the derivative of 1x, well, we know that equals just 1. And I take that and I times it out the front. But I don't subtract 1 from the power, okay? So next to this example in your book, let's write those as worded steps. So step 1 is differentiate the power. Step 2 is multiply out the front. And step 3, don't subtract 1. From the power. And that's it. There's your steps. So, pause the video if you need to get that down, but let's have a look at some examples now. So we're going to differentiate the following. All right, so let's have a look at these. Okay, so I'm just going to talk through these and then I'll give you a bunch to have a go at on your own. So the first one, if we follow our rules, we differentiate the power and times it at the front. So my derivative, I'm going to do y dash this time. Derivative of the power is 2, so I get 2e to the 2x. Easy. All right, the next one, when I differentiate the power, I still just get 1 this time. So 1 timesing out the front, well, that still just gives me 2e to the x. Differentiate the power, times it out the front. I'm going to have negative 2 as the derivative, times out the front gives me negative 6e to the negative 2x. And the last one, definitely a trick to it, because it's remembering our derivative rules from our calculus topic earlier in the year. When we have two functions multiplying by each other and they have x in both functions, we need to do the product rule. So it's a bit of a flashback. So remember, we call the first one u, second one v, and our product rule formula is VUV, vu dash plus uv dash. Remember I told you I want to see u equals, u dash equals, v equals, and v dash equals always, always. Okay, so x and e to the x. Differentiate x, I get 1. Differentiate e to the x, I get e to the x. Sub it into my formula, y dash. Actually, I didn't even call this function a name. It's going to be, okay, v e to the x timesing by u dash, 1 plusing with u, which is an x, timesing that with v dash, which is e to the x, which gives me an answer of e to the x plus x e to the x. And as we spoke about earlier in the year with these final answers for product and quotient, often they'll put them in a factorized form. So there's my derivative. So they're obviously going to get some harder ones of this, where we bring back some more differentiation rules like chain rule and product rule. So it might be worthwhile flicking back to your summary or your notes in your book. But let's say pause the video and give this one a go. Let's go 3e to the 2x over x squared. I want you to find the first derivative of that one, please. If you finish that first one, give this one a go. Okay, pause the video. I'm going to display my solution in a moment. Okay, so This one, we had two functions with x in both that are dividing, which we know is our quotient rule. So our quotient rule formula is VAV, but we minus, and it's all over v squared. So plugging everything in. Remember, quotient rule, you can also do the product rule by bringing the x squared up. So if you did do the product rule on this one with 3e to the 2x times in with x to the minus 2, that would still give you the correct answer in the end. Okay, you just got negative powers, which aren't always the nicest things to deal with. But if I factorize this, I can bring a 6x e to the 2x out the front of both of those terms on top, which leaves me with an x in here and then minus 1 all over x to the 4. Now everything on top is timesing together. I could cancel one of the 4's x's here with one of the x's on top, which gives me a final answer of 6e to the 2x outside of x minus 1 all over x cubed. Hopefully I've made no errors there. I did zoom through that one quite quickly. And the last one, it was our chain rule. Okay, so again, I forgot to label it with a function. We'll call this one y equals. So y dash. Chain rule, take the power, times it out the front. 6e to the 2x minus 1. Minus 1 from the power, then times by the derivative of the brackets. So once I do that, I get 12e to the 2x out the front, outside of e to the 2x minus 1 to the power of 5. Okay. I'm going to leave it... Actually, no, let's keep going. So you'll get a chance to practice a heap more of those, but the next part is, I'm going to call this next question G. It's still, again, something from our calculus topic earlier in the year. So we're going to find the gradient of the tangent and the normal to the curve y equals e to the minus x at x equals 2. So remember, this is where we learn about that distinction between the fact that our gradient function is our first derivative. So if we want the gradient, we start by differentiating the function. So let's differentiate y equals e to the minus x. So the derivative of that is equal to negative 1 e to the minus x, or just negative e to the minus x. So once we differentiated, this is our gradient function now, we can now find the gradient of a tangent by subbing in the x value. So then we would say, therefore, m of t, t being the tangent, equals, and subbing in our x value of 2 in where x goes, negative 1 e to the minus 2. If I clean that up, it's going to be just negative e to the negative 2, which I could still clean up again and say that's the same thing as negative 1 over e squared, which I think is a bit nicer. So that's the gradient of the tangent. So you find the gradient of the tangent by differentiating the function, subbing in the x value. But then we looked at gradient of normal. Remember, if I have this function, which we know looks like this, what I've just found is the gradient of the tangent at x equals 2. So if 2's here, what I've actually just found is the gradient of that line right there. That's what that answer here is. So what we're going to do now is do the normal, which is the perpendicular line here. So let's hope we get a positive answer, because we need one, because the gradient of that normal is positive. So I take my derivative again, and I've subbed in my x value, and I've gotten this for my tangent. Now we know that the tangent and the normal are perpendicular to each other. Where we looked at these formulas, there's two formulas, that the m of the tangent times by the m of the normal together will always give you negative 1. But also that the gradient of the normal is equal to negative 1 over the gradient of the tangent. They were two formulas we looked at earlier in the year in terms of our parallel and perpendicular lines for the tangent and the normal. But we said there's a much easier way. You just take the reciprocal, so you flip it upside down, and then you take the negative, okay, so or opposite sign. So that will give us the gradient of the normal. So if we take our gradient of our tangent, flip that upside down and take the negative of it. So the gradient of normal is going to be negative of that upside down. Gives me e squared on -1. Two negatives make a positive, and then anything over 1 is just itself. So the gradient of that normal is e squared. So when you're asked for the gradient, all you have to do is differentiate, sub in the x value. That's your tangent's gradient. So if they ask you then for the normal's gradient, you just take the negative reciprocal. So the last part I'll show you is then if we were to go with, let's go down here, h. Okay, so what we need to find now is the equation of the tangent and normal to the curve y equals 3 to the power of x at x equals 1. So this time, notice the difference in the wording. We want the equation rather than the gradient. All right? So when we have to find the equation, we do everything we just did to find the gradient. So you differentiate, sub in x, and that will give you the gradient of the tangent. Tangent. Then you use the point gradient formula. So again, look back in your notes from earlier in the year. We did do this. And that will give you the equation of a line. So let's start. Let's go with, I'll stick with the theme I did before, blue for tangent. So if I differentiate, y dash gives me 3e to the x still. So then m of the tangent, subbing in the x value, just gives me 3e to the power of 1, which is just 3e. So if I want now the equation of this tangent, I now use my point gradient formula. Y minus y1 equals m outside of x minus x1. The only thing though I'm missing is the y value at this point. I need a point and a gradient to sub into this formula. I got a gradient here, 3e, which will go where m is, but what I'm missing is a point. I have an x value. What I need to find is a y value that's corresponding to that x value. So if I sub that x value into the original equation, I'm going to get y equals 3e. There's my y value. So the point that this curve passes through is 1, 3e. All right, so now I have this point. I can use it in my point gradient formula. So I get y minus the y value, which is 3e, which is coincidentally, not always going to happen, the same number as our gradient, and then my x value. Clean this up and you can put it in general form or y-intercept form. I didn't specify here. So if I do just chuck everything over the other side and have y equals, I'll have 3ex minus 3e, then bring the negative 3e over and plus 3, oops, that should be an e, and plus 3e. My final answer is 3ex. So there's the equation of the tangent. So now if we want to do the equation of the normal, this time we go from our gradient of our normal. We know the gradient of the normal, flip that upside down and take the negative. So I'm going to have negative 1 over 3e. So now put that into my point gradient formula. I get, with the same point, you can use the same point we've already used, y minus 3e equals negative 1 on 3e, x minus 1. Now remember, back at the beginning of the year when we first looked at these questions, when there was a fraction on our gradient, the best way to do this was to take that denominator over and times it on the other side, rather than trying to expand a fraction. So if I do that, I'm going to have 3e outside of y minus 3e is equal to just a negative 1 outside of x minus 1. So you don't have to do that, but it just eliminates the ugly fraction. So then I end up with 3EY minus 3, actually that'll become 9E squared, 3E timesing by negative 3E, is equal to negative x plus 1. And this one, it's ugly, so I'm just going to put it in general form. General form, we need x to be positive, which gives me x on this side becomes positive, plus 3EY minus 9E squared minus 1. And that's our equation of a normal. Okay, so some of those do get pretty tough at the end, but it is a bit of a blast from the past. See how you go with the exercise now, where you'll practice those over and over again. Okay, so I'd like you to have a go at exercise 803, just questions 1 to 9. But I'm going to be mean here, I want all letters from questions 1 to 9, please. See how you go.